Hello and welcome to another video. In this one, we're going to be talking about copy on write. Now, I just did a video about fork versus spawn and introduced the concept of copy on write. So watch that full video for the full details of what that's about here. We're just going to do a quick little intro of what copy on write is. When you fork a process, which is one way that you can create new processes on POSIX-like operating systems, it will share parent memory sort of automatically. And as you write to it in the child process, it will get copied into that process before written. So basically this means that any memory from the parent process, if you're read-only accessing it, you get it for free. You don't need to have that memory in your child process. Now, unfortunately, Python doesn't really benefit from this all that much unless you use this one little trick before you fork. In order to show this, in order to describe why this is a problem, we need to take a look at the implementation of the garbage collector in Python. Now, I know, this is low-level C shenanigans, but trust me, it's actually pretty easy to understand what's going on here. So every object in Python, this is CPython, of course. PyPy does this completely differently. Every object in CPython is a PyObject star pointer thing. And the way it is stored is there is the PyObject star, which is kind of your type and other stuff there. And right before it, there is this little struct called the gc head, which gc here stands for the garbage collector. And this is where the garbage collector stores state about the object. Now, unfortunately, whenever the garbage collector runs, it modifies these two variables. And the garbage collector runs all the time in Python. Occasionally it'll decide to run when you free objects or when functions end, or you can sort of tune when it runs a little bit, but generally it runs at unspecified portions while your code is executing. And what this results in is if you're using copy on write and all of your objects are getting modified, you're not really benefiting from copy on write at all, because every object is going to get paged in by the garbage collector. Just to show this, I am going to make a small little program which imports a bunch of modules just to have some resident memory, then uses multiprocessing to make some child processes, and then we'll take a look at the executing processes to see what memory they're actually using. So in order to get that, let's do multiprocessing. We're going to import the garbage collector just to explicitly call it to make this a little bit more deterministic. And we're also going to import some other modules to make the memory bigger. Let's actually get this going. Also we're going to do time. We're going to freeze the process in place such that we can actually inspect the memory while it's running, because otherwise it's just going to start and stop really quickly. All right, so we're going to print starting with multiprocessing.pool. Just going to make a multiprocessing pool. And we're going to run p.map on a silly square function. Let's just, yeah. Is that the right number of parentheses? Hopefully. Def square x int to int return x times x. And we're going to import some modules that I know happen to take up a bunch of memory because they import a lot of other modules, async IO, SSL, and C types. Okay, the other thing I'm going to do is we're going to sleep inside each of these child processes, time.sleep 15, and we're going to run the garbage collector just to force it to run to simulate a long running process. You can imagine like a web app where you spin up your primary, let's say, UISGI worker, and it forks off all of your child workers, and they'll serve web requests, but eventually they'll run the garbage collector. So we're just going to do this up front to make it more clear what's going on here. Also need to return 0 down here. We should have a working program. Yeah, okay. Leave blank lines, ignore that. Imported modules intentionally. All right, if we run this now, we're going to use a tool called smem to take a look at the running memory. Oh, that's going to get real small. Yeah. And we're going to do a pattern. We're going to make sure the pattern doesn't match itself because smem is actually implemented in Python. So we're going to do this. And we're going to see a few values here. Let's actually run it again so you can see it on screen. Oh, I was not quick enough. Okay, so this is the normal execution of the code. There's a whole bunch of numbers here. The one we're interested in today is this USS number. What USS stands for is unique set size. This is basically a representation of bytes, or I think it's actually pages or kilobytes, or I don't know what the actual unit is. But it's some unit. It represents the memory that a program uniquely has. So this means stuff that is not shared memory from the parent. It's actual memory that's been paged into this process. And it's unique, meaning that some other process doesn't share it. PSS is the proportional shared size, which somewhat represents shared memory, but kind of doesn't. I feel like it's really hard to explain this number, and I spent about I spent about 15 minutes trying to understand this before making this video, and I don't have a good explanation for it. So we're going to ignore PSS. RSS is the resident set size. This is basically what TOP or other programs will report as the total amount of memory that a process uses. Note that this doesn't necessarily represent the physical memory used, because there are shared pages from parent processes. And you'll see here, this number is very different from the resident size. We have about 5,000, I think it's kilobytes. We'll say it's kilobytes. We have 5,000 kilobytes, but you can imagine there's about 8,000 kilobytes here that are represented as part of your resident set size that aren't necessarily paged in, probably shared from the parent. And this is kind of the default case. So keep this number in mind. We are now going to use a little trick which prevents the garbage collector from paging in those objects. And we are going to do gc.freeze. This is a new function that's available in Python 3.7, and it does some sort of magic to move all of the current objects into what's called the permanent, I believe it's called the permanent garbage collector phase. No, what is it called? Stage? Generation. That's what it's called, because Python's garbage collector is a generational garbage collector. So gc.freeze will put things into a permanent generation. This means that they don't participate in garbage collection after that, and so they'll kind of remain stationary in memory. And so now if we do this same little exercise here, you'll notice here that our unique set size went down significantly. So it's now only 2,000 of kilobytes or whatever. You'll also notice this PSS went down. I can't really explain this all that well, but the important thing to note here is because we froze the garbage collector, we were able to reduce the uniquely paged in memory in child processes. Now, there is still, we did very little work. We just squared a number, and still we pulled in 2 megabytes of unique set size. So there's some other stuff that's happening here. There's ref counts that are getting incremented and decremented. A whole bunch of code had to run to necessarily do this. So it's still not a complete fix for this problem because ref count is stored on the object as well. So anytime ref counts are incremented or decremented, you'll page in that object also. So it's not a silver bullet. It doesn't solve all of the problems, but it definitely will reduce your memory usage when you're forking an application. This was actually used at Yelp as a pre-fork operation. So pre-fork being, you spin up your app, you do a bunch of work, you cache some values or whatever, and then any child worker that gets forked from that inherits all those cached values. So you might be able to do a bunch of, like, maybe you look up some common, in Yelp's case, maybe you look up like common neighborhoods in New York or something like that, or the boundaries of regions in Australia or something like that. Maybe that's something that you need in your app all the time. You can freeze those objects and freeze all of the modules that are already imported at that point. That way they don't participate in garbage collection going forward. This also speeds up your app a little bit because garbage collection takes time, and anything that's in that permanent generation isn't being checked for liveness and collecting. But anyway, that's gc.freeze and why copy on write in Python doesn't really work all that well. I'm actually going to do another video about a new feature that might make this better in the future, but that'll be a future video. Anyway, hopefully you found this useful. If there are additional things you would like me to explain, leave a comment below or reach out to me on the various platforms. But thank you all for watching, and I will see you in the next one.